Welcome everyone to this month's this month's webinar, which is about the Hipot test. This is one of our most highly attended ones, so there's a lot of relevant information that people are looking to get. So hopefully after this webinar we've answered most of your questions, and if not, we'll have a Q&A at the end. I want to introduce our team first. Even before that, I want to apologize in advance in case I do cough during the presentation, just getting over a small bug, but hopefully it shouldn't be an issue. So first, myself, I'm Anthony. I'll be your presenter today. Application engineer here with Associated Research. Next we have Bashan, who's our panelist, also on my team. And next we have Brittany, who is our organizer. Any questions or issues that you will have with this presentation? Of course this pops. Feel free to ask Brittany if you want a copy of the presentation. If you're having issues hearing me or seeing me, she will take care of you. And anything else technical question wise, feel free to reach out on the chat box to Bashan, and he'll make sure you get taken care of. So what will we cover today? Today we are going to discuss understanding the Hipot test, right? What is the Hipot test? What's its purpose? Then we'll talk about how it's performed, what's physically happening when I'm running a Hipot test, as well as understanding the parameters. What do the parameters mean? My limits, how do I set those limits? We will compare AC versus DC testing, right? And how do I go back and forth from one to the other if I need to? A lot of standards will say, you know, if you cannot pass your AC one, you can do it in DC. Why? We'll get into the 500 VA Hipot testing. So a lot of standards will call out that your Hipot tester at least have that type of power rating. And then we will get into some specific associated research features for DC testing. So first, let's begin with the Hipot test, okay? It is called the dielectric withstand test, dielectric voltage withstand, dielectric strength test, Hipot, which obviously stands for high potential, and I believe in Europe it's been known to be called a flash test. Hipot test is the most common type of electrical safety test. What it is designed to verify that the installation of a product, whether that be a material, a plastic, or just air, if that space or material is adequate enough to withstand high voltage, right? The test is performed by stressing the insulation of the product far beyond what it would encounter during normal use, hence the term voltage withstand test, right? So if this test can overcome thousands of volts without the insulation breaking down, then we have peace of mind that our product will be safe for our end user when they plug this into, you know, steady state 120 volts, 240 volts, what have you. The takeaway from this slide is the Hipot test is performed at high voltage to test the insulation of a product. Okay. So this diagram pretty much shows you what's happening during the Hipot test. It's we can see our Hipot tester on the left of the screen, and our DUT is on the right of the screen. We have my high voltage here connected to line neutral shorted of my device, right? You can see here the resistance that symbolizes what the impedance or the circuitry of between your line and neutral. And then we have our return connected to the ground circuit, right? Via a ground point on the chassis. And between that, what do we create? We create a bit of a capacitor, right? Two circuits parallel to each other with insulation in the middle. And so we are testing that space there. Okay, the resulting leakage between that capacitor, right, through the insulation is measured to determine whether a product's insulation is able to withstand the high voltage without breaking down. So we will get to the definition of breaking down in the next few slides. So this test again verifies that the insulation of a product is capable of protecting the user from any leakage currents as a result of an electrical fault within the product. So again, leakage current gives a measure of the product's insulation quality. There's other tests that also perform this insulation resistance test, but we'll get to those in other webinars. But today we'll just focus on the Hipot test. Okay, so here we have a bit of a graphic, an illustration of what's happening during a pass. The insulation is actually able to withstand this high voltage and does not break down, nor does it allow excess leakage current to flow on the surface of the product. Okay, so ideally, as desired, we would be applying this high voltage to my line neutral, and now we're returning on the ground circuit, right, applying an electric field between this insulation. Okay, so now I have an electric field. I am giving current or electrons the juice to break through, to flow through, right? And so now we're testing this insulation. Can you stop these electrons from breaking through this barrier while I'm giving it so much force, so much power, such a strong electric field? If it can, then you've ensured that your insulation has quality. It did not allow excess leakage, and it's a pass. Now on the other end, if insulation breaks down, if that electric field, if that voltage applied across the insulation is strong enough to have that electron, not just that one, but excessive amount of electrons break through that insulation, so much current that my transformer can no longer supply it, well, that transformer is going to shut itself off because, hey, I'm going to be in this overpower protection state where I've given you everything I can. That insulation is helping me in no way. It's become a breakdown. So much current has tried to leak that I cannot provide anymore. Your insulation has failed. That's pretty much the definition of a breakdown. Poor insulation will break down and dangerous leakage current can flow on the surface of a product. So that is our definition of how you would fail a Hipot test. Now there's other failures you might see. There's parameters that you set, right? Maybe I don't want to wait for a breakdown. Maybe if that leakage occurs at 2 milliamps, 3 milliamps, well, you can set those limits and you'll see different types of failures, which we'll talk about in the next coming slides. So when performed as type tests, Hipot tests are helpful in finding various important defects. Nicked or crushed insulation, stray wire strands, or braided shielding. So what do we do? I mean, at the end of the day, we're not only identifying if our insulation is good, but also trying to burn off some impurities, right? Do I have some metal, shards? I don't want to say shards, but just small pieces of metal that are sitting on the insulation, or can be burned off, can actually conduct, right? We can burn that off. That's sometimes a lot of companies perform a burn test, a burn Hipot test. Let's run it once. We might expect to fail because of some impurities that are lying on our insulation and our circuitry. All right, now that we've burned that off, retest it and we'll see a pass. So this also identifies spacing problems, right? Tolerance errors in cables. A lot of PCB manufacturers have this issue, right, where they need to make sure there's a certain amount of spacing between their boards to make sure no arcing can occur and damage those very sensitive components. Inadequate creepage and clearance distances introduced during the manufacturing process. This is also something that you can catch with a Hipot test. So it is a very versatile test. Now that was type testing, right? That's more R&D. That's more what in standards is called performance testing. Now if we're talking about production line, which standards will say it's production, it's used to determine whether the construction of the product, or I'm sorry, of the unit is the same as the one you designed during that type testing phase, right? In production, it's usually a lot quicker, right? Maybe a 1-second test, as opposed to when you're in that R&D stage, your UL or TUV or ETL auditor says, you have to do it for 60 seconds as per the standard you're testing to. Such a failure could result from a new operator in the winding department. Exactly, right? Quality. You're checking for quality. You've already designed a good product. Now you want to make sure the quality behind your manufacturing process is up to par with that of your performance testing. So in production, it's more of a no-go test, right? It can be used to find various quality issues. Again, you know, something like fraying on the wires on the left, right? That can leak to ground. Some current can leak to ground and trigger a GFI failure, or it can find some path through that insulation that has now caused a breakdown. So a Hipot test can identify scrapes, pinholes, spacing, crimps, heat material buildup, some moisture, right? A lot of the process in making some heating elements involve baking the DUT, right? So you want to make sure that all that moisture has dissipated or is gone from your product. A Hipot test can help you identify that. Also, quality over time, right? We design our insulation and we know it's great on day 1, but what about on year 10? You know, has that insulation degraded? There's various methods of testing that. So the best indication of a dielectric breakdown is a leakage current measurement, significantly higher than the nominal current measurement, right? So you've designed this product, you've developed it, you've gone through your performance phase, you're now in production phase. You've identified kind of the characteristic of your product. You know it, you know, better than your operators do. You understand, yes, it does leak. Everything leaks a little bit, you know, and some things leak a lot. You want to stay out of the I leak a lot category, right? And so setting your limits, which we'll discuss a little bit later in the slide, is a good way to develop uniformity among your products. The test voltage, well, that test voltage can impact the product that you're testing, right? Is your product highly capacitive or inductive? You might get some false failures due to the characteristic of your DUT. You know, do you need to increase your ramp time because you are drawing a lot of charging current due to the capacitance of your product? Do you want to make sure you have a ramp down time because you don't want to leave a charged product that passed left for your operator to grab and potentially create a dangerous situation? So when we, as I'm saying, right, when we perform a Hipot test on a product, we think of the product as a giant capacitor, right? I have my line and neutral shorted, that's one plate of the capacitor, and I have my ground circuit, that's the other plate of the capacitor. What we're testing is in between. So hence the voltage applied between the mains and the chassis of the product, which are separated by the insulation, such as a capacitor. A lot of DUTs that are purely resistive, then you can get away with just applying to one side of the line neutral. So how do we're kind of getting into parameters now, right? How do we set our test voltage? Now, we get a lot of calls from customers with this question. I've just bought my instrument, I've turned it on. The default is at 1.24K. What is it supposed to be at? What's my high limit supposed to be at? Well, these are questions to pose to the standard you're testing to, and these are also questions to pose to the lab you're certifying with. Okay, now most standards will state for the Hipot test 2 times the rated input voltage plus 1,000. Now in the US, most input ratings are 120 volts, so 120 volts times 240 plus 1,000. That's why our instruments come defaulted with 1.24 kilovolts. Now, in some cases, safety agency requirements call out for higher voltages. For example, on medical equipment, if you have applied part, if I have some sort of probe or applied part that is on my body or will be touching my body, this is direct contact with the human, right? If there's leakage current on that applied part, well, it's worst case scenario, right? It's literally touching a human being. So for those applications, the voltage is much higher, up to 4,000 volts. Most double insulated class 2 products are subjected to design tests at voltage levels much higher than the rule of thumb I described earlier. Now, there's DC testing, right? Right now I'm pretty much talking for AC. Okay, we'll discuss DC a little bit in the next coming slides. But again, if you're ever confused about what you should be testing to, just keep in mind 2 times what if you're at 240, a lot of products now are made between 100 and 240, right? So you'd be at 1480. That would be your test voltage. So let's take a look, for example, at IEC 60601-1. This is for medical devices. The dielectric strength test is called out in section 8.8.3. It says test voltage refer to tables 6 and 7, which I'm sure would state either twice the rated voltage, unless we're talking about an applied part. Then we would be talking about that higher voltage. Test time states a 10-second ramp up, a 6-second dwell, and a 10-second ramp down. And we're tested at 50 to 60 hertz, whatever your product is rated to. And here's where we figure out how we get our DC voltage, right? We would multiply that AC, the RMS value of that AC, to get the DC equivalent. So your AC voltage, 1240 times 1.414, which is usually in the 1780 range. And what's your pass criteria? So this is an important part. As I said earlier, most standards will say no breakdown shall occur. Well, that's fine. That's the minimum you can do, right? No breakdown shall occur in my product. That's what I need to do to pass 60601-1. That doesn't mean your internal standards, the internal quality you desire for your product, isn't greater than that. So if I test 10 products and I know they leak, 8 milliamps, well, that's way too much for me. So I'm going to go back. They're not breaking down, but as far as the quality that I expect of my product, that's too much. I'll go back and redesign it to the point where I'm comfortable with a certain leakage current, 2 milliamps, 3 milliamps. Okay, once I've identified that range that I'm comfortable with, well, now I'm going to set my low limits and high limits accordingly to make sure all my products are uniform. So there's a couple different types of products out in the market, right? The 2 main categories are class 1 and class 2. So what's class 2? Well, class 2 only has your line neutral, and your class 1 will have all 3 of your circuits: your line, your neutral, and your ground. So it's pretty easy when you're doing a class 1 product how you would run this test. I would short my line neutral as I have here. Obviously this is just to kind of demonstrate how this is done, but there's better ways to do this than just clipping it to the line neutral of your plug. So I'm applying high voltage to my line neutral, as some of our previous diagrams explained, and I'm returning on the case or on a ground stud that's sticking out of the rear of my product. Well, that's all well and good, but what do you do when you have a class 2 product? So I want to quiz you guys really quick on that situation. I have a class 2 product, does not have a ground circuit, yet still requires Hipot testing. IEC tells me I still need to test this. This is a common question we get a lot. So how can this be performed? I'm told to short between, I'm trying to test the insulation. All right, short between your mains and the other side of your insulation, which is usually a ground circuit. I don't have a ground now. So I'll let Brittany open up that question and see what you guys think.
Hi everyone. So the poll question is a Class 2 product does not have a ground circuit yet, still requires Hipot testing. How can this be performed? So select one, apply high voltage to the line while returning on neutral, high voltage to the line neutral shorted while returning on ground instead of Hipot, put DUT in saline, high voltage on the line neutral shorted and return on saline, or wrap the DUT in foil, apply high voltage on line neutral shorted, and return on foil. So I'll keep this open a little longer.
Sure, thank you, Brittany.
Sure.
So what I mean by put DUT in saline, I mean I'm dropping my product in a conductive liquid, right? Some sort of conductive solution, and then dropping the electrode in that solution to potentially, I guess, see if any leakage current, if that's the proper way to do it, right? Apply HV to line while returning on neutral. Well, that would test insulation between what components are on that product. HV to line neutral shorted while returning on ground instead of the Hipot.
Hey
And then,
Tony, we have the
sure,
answers in.
let's do it.
So 18% went with the first answer,
Okay.
28 with the second, 2% with the saline answer, and 52% with the foil.
All right, awesome. Thank you, Brittany. So we can discuss these results. So 18% say apply high voltage to line while returning on neutral. Well, you definitely don't want to do that because depending on how much current capability your Hipot tester is, you're pretty much powering on your instrument with thousands of volts. You know, and that's definitely going to damage your instrument. I'm sorry, your product. Um, High voltage to line shorted while returning on the ground instead of the Hipot, that's just going to trigger a GFI failure. All the current is not returning through our well, actually, let me think about that. Actually, you're just going to pass. You're going to pass because you're just testing the air in between the ground of the Hipot tester and the mains of your product. So there's nothing but air in between those two circuits. So you're probably going to pass a Hipot. You don't want to do that. You do want to pass, but you want a true pass. So it is interesting. You know, the correct two answers are actually the last two. A lot of companies do pour their DUTs in some sort of saline conductive solution, have an electrode inside that solution while applying high voltage to the line neutral of the product, right? So any leakage that would leak through the case, well, now it's being collected inside that conductive liquid and returning to the return port of the Hipot tester. Now, that's very tricky application. It's important that the tough part is creating that space where you're dipping your product in, but somehow isolating the line and neutral of the product with high voltage applied to it and hope it does not arc into the solution. And the most common way, as we saw 52% of our attendees answered, was to wrap the DUT in foil, apply high voltage to line and neutral, and now you can just return on the foil. In essence, right, you're making a quasi-ground circuit for your product. So I'm glad, right, we got some good feedback and some people learned a little bit more about that other application of using a saline solution. Okay, thank you, Brittany. So let's talk about some of our failure detectors. Excuse me. A breakdown. As I stated earlier, a breakdown is a complete breakthrough of current through your insulation. This is a quality issue. This is potentially a design issue. But in essence, I know that that insulation cannot protect, well, maybe it can protect, right? Maybe, sure, you failed at 1,240 volts, but you know, maybe at 500 volts it would have passed, at 1,000 volts it would have passed. But you know, fortunately we have these IEC standards that regulate what the definition of a quality product is, what makes it safe for you to use. And so while a lot of people maybe try to be a little more economical on the insulation they purchase, it still has to meet that minimum criteria of not breaking down at that voltage. So a breakdown, as we showed earlier, is just a large, complete failure of the insulation. So much current is now drawn by your product's insulation that the Hipot tester cannot supply anymore. You've now reached the power capacity of the transformer inside your Hipot tester to the point where now it's got to protect itself. I don't want to, the more I can probably output more current, but I might damage myself. So let me shut down and let the user know, hey, you just had a breakdown. All right. Leakage limits. So this is what I was referring to earlier. I know my product passes breakdown. It passes Hipot. It does not break down, but I want to maintain uniformity among all the insulation on my products. And so if I'm testing 100 pens and I know the average leakage of a good pen is 2 milliamps, well, guess what? I'm going to set my high limit to maybe 2.5 milliamps, 3 milliamps. I'm also going to set my low limit. Now, why set a low limit? What's a low limit mean? It means, hey, I better at least see X amount of leakage. Why would you want that? Why would you want leakage to occur, right? You want your insulation not to leak at all. But that's just, in reality, that's not possible. All insulation will have some leakage. And so if I'm saying, hey, I know the average leakage of a known good product is 2 milliamps, well then let me set my minimum to 0.5 milliamp, because I know I'm at least going to see that much, right? So what happens when you don't see 0.5 milliamp? You get a low limit failure. So what does that tell you? That tells me my operator forgot to connect my return, or forgot to connect my high voltage lead. And so you would have no other warning. If your operator were to forget to make proper connections, your Hipot test is going to pass, because now it's just testing what I had said earlier, right? The mains of your product against a bunch of air, wherever the air between wherever your return clip is at, and it'll pass. And you never truly ran a Hipot test on that product. So that's why we kind of stress that using a low limit is very important. And also for peace of mind, going back to the high limit, I said I'd set that to maybe 3 milliamps. So if I leak 4 milliamps, 5 milliamps, 6, it's not a breakdown, right? I still passed a Hipot, but I want to know what has changed in my manufacturing. Why am I all of a sudden getting a little bit more leakage? Even though I'm still passing, it's just gives you peace of mind, uniformity among all your products, that you know what to expect, right? Because if you're not seeing any breakdowns, but hey, this one leaks 1 milliamp, this one leaks 8 milliamps, 10 milliamps, you're all over the place. You have no consistency in your manufacturing. And excuse me, sorry about that. We have arc detection. So arc detection is a tricky one. We get a lot of calls on this. And because we have a lot of calls on this, we've created a white paper, a paper to help us out and explain to the customer. Now this is 2-3 pages long, but we'll just look at this table for now. This table states what exactly, sorry about that. Where did we go here? What exactly is occurring? Arcing is a temporary condition due to imperfections in the insulation that may be seen as a flashover or corona, right? So it causes brief spikes in leakage current measurements. They may occur in products that are still electrically safe depending on the testing standard. So arcing doesn't mean you failed your Hipot test. It doesn't even mean that you currently have bad insulation. It could be a sign of potential degradation happening over time, but really it's just this instantaneous discharge or flashover of current. And when you're in your performance testing, that's the type of information you want to know, right? If you're seeing a brief spike in leakage, well, you may want to consider investigating a bit further on the characteristics of your insulation. So this is why we've added this feature into all of our Hipot testers. Does this mean that everyone uses it? No. Does it confuse everyone? Probably. But for those who want to just have a better understanding of the characteristic of their insulation, it's a great tool to have, because arcing comes with different sensitivity levels. For most of our instruments, excuse me. Now, for most of our instruments, those levels go from 1 to 9. If I'm at a 9, 9 being the most sensitive, if I see arcing that reads at about 2 milliamps, I'm going to fail you with an arc detect fail, with an arc fail, is what most of your instruments would say, right? If I'm at level 1, well, guess what? I'm going to allow arcing to occur until, let's say, 20 milliamps. Okay, so now you can kind of identify, I know I'm getting arcing, but what level of arcing am I getting? And so with these levels, you can kind of identify the exact type of current you're seeing during this arcing, and that can help you make the decision, okay, is this arcing a bit too dangerous? Is it a bit too much for comfort? Do we need to redesign, or is it only a couple milliamps here and there? If I'm failing at 9, am I failing at 8? Oh, I'm not failing at 8. I'm only failing at 9, the most sensitive level. So I'm fine with it. Where breakdown, on the contrary, does mean a Hipot test failure, right? Arcing, if I didn't mention it earlier, you can arc all day long. As long as there's no breakdown, most standards will say, you're fine. Hey, we tell customers, if you're in production or you're not testing to a standard, you can just turn arc off. Now, breakdown, on the other hand, is a catastrophic insulation failure condition that becomes evident at lower voltages during each subsequent test, right? So I've just broken down at 1,000 volts. Current has now broken through, found a hole, found a path to the return. Well, now that that path is there, I'll probably break down at 200 volts less. That's kind of what you're really looking for, right? That causes excessive and dangerous amounts of leakage to flow through the insulation. And it's always a sign of a faulty product that isn't fit for production or sale. Well, always is a strong word. I think, if you have a breakdown, it might have been, like we said earlier, maybe some impurities burning off. And if you run it again, you might pass. So it's always good to do a burn test. Or if you fail it, retest it again. You may have just had something in the air gap, maybe some scraps of metal in the air gap between boards, or something on your insulation that drew current, right, burned up, and now it's gone, and now you can pass your test. So we went over breakdown, leakage limits, and arc detection. Now I want to discuss AC versus DC, right? Depending on the product being tested and the test standard, a Hipot test can be performed within either way, right? AC or DC. I think the DC comes into play when you have a highly capacitive product, and the constant oscillation of voltage is creating all this charging current, which is making you which is making you fail, right? When you really should be passing. It just happens to be that you have a highly capacitive product. That's no dig at your insulation. That's just a characteristic of your product. And so you can now perform a DC test, right? Well, you still have issues there, right? Excuse me. Because in that first moment, when you go from 0 to 1,500 volts, well, you're going to get large leakage, large charging current there. Now, once you've peaked out and you have a steady state voltage, well, you've lost all charging current. It's all purely resistive leakage, and you don't have to worry about failing your test. So luckily, we have some features that I'll discuss later in the DC test that help you avoid failing during that ramp time. It's important to understand the difference between the nature of AC and DC voltage current, and we'll get into that a little later when we talk about those special features we have built into our DC tests. But getting a little bit deeper into what your leakage looks like, right? A leakage current that is measured by most AC Hipot testers is a vector sum of the resistive leakage current and the reactive leakage current. That reactive leakage is what I was referring to as a charging current, right? Capacitive current, imaginary current, if you want to call it. Some associated research Hipot testers are capable of displaying real and total leakage currents for manufacturers who require this extra information. So here's our vector sum of how we tabulate that I total, right? You have your capacitive current, your resistive current, and we will show you your total number. Now, if you only want to see the real part, we have features or methods of only displaying that. But it's important to understand the nature of your DUT, of the product you're testing, right? You may be failing, but your product may be good. You're just not giving it enough time to either have less charging current or reactive current. So because you have such a short window and you're changing voltage at such a high rate, and that reactive current is very high, so now you're getting false failures. So again, all we're worried about at the end of the day is resistive current. That's what can be harmful to our consumer, and that's the true leakage that's breaking through your insulation. Okay, here we will look at our graphic. You can see as the voltage increased, your real current increased as well. Leakage current is straight current, right? It's flowing through the insulation. The IR is actually the purely resistive current on the right side of the circuit here. You can see, right? This is the actual current that we want to read. That's actually being used, right? When we have a product, right? Now I'm talking about power factor, right? What's actually just being eaten up by the capacitance of your product, and what's actually doing work, right? Well, that doing work is gonna shock our consumers, or at least that's the leakage we care about that the IEC standards are referring to. And so we want to limit that resistive current. But unfortunately, all products have a little bit of capacitance to them, or a little bit of voltage dropped, and so we do get that charging current or that capacitive current, and we want to minimize that effect on our test results. So again, some AC Hipot advantages and some DC Hipot advantages we can go through. Now with AC Hipot, there's no ramping involved, meaning you can run your test quicker, right? You don't have to wait and ramp up to avoid that charging current. AC voltage naturally ramps up, right? It oscillates. So you don't have this huge window during your ramp up time, or I'm sorry, the small window during your ramp up time where you're seeing huge spikes of reactive current. So no ramping is involved in AC. Discharging the DUT for the most part is not necessary because it's just charging on its own, right? It's oscillating. Insulation is stressed in both polarities, so in the negative and the positive. At the same time, if I'm testing at 1.24 kilovolts, well, it's also, depending on the frequency, for a certain amount of time, it's seeing a lot higher voltage than that, right? So some might view that as an advantage or disadvantage, that you're testing a little bit more strenuous in AC. You can measure both the real and reactive current. Maybe you don't know the capacitive nature in your product. Running an AC Hipot test, that'll give you some insight in how that reacts. Commonly accepted by safety agencies. For the most part, it's kind of the first go-to. AC is the first go-to. Okay, but if you're seeing way too much reactive current, well then they'll say it's okay to run this test in DC. So that's one of the advantages of DC, right? It can be performed at a much lower current level with less risk for operator. Usually in DC, during the dwell cycle, while I'm actually performing the test, my leakage is going to be slim to none because that's the purely resistive leakage, right? So it's less harmful for any operators. it's often easier to perform on a capacitive test. Now we've made it easy. We've made it easy due to this ramp high and charge low feature, which we've built in to most of our testers for you. Otherwise, with some older testers, if you run a DC test on a highly capacitive product, you're going to instantly fail every time because your ramp up is so slow, your ramp up is so fast that you're creating a large amount of reactive current, so much that your meter can't even measure, and it's going to say, I think I just saw a breakdown because a large amount of current was just drawn from me. But there are a DC Hipot advantage is that they're cost effective, right? They're usually single box, one type of test, and easily to move around from test station to test station. But again, they're not always accepted by safety agencies. Now that's from standard to standard, you know. Again, not always doesn't mean that the majority of them. The majority of standards, I think, will allow you to test in DC if AC keeps failing you due to that reactive current. Now let's talk about 500 VA testing. In the past, a lot of standards would call out that the generator shall be able to supply a power of at least 500 VA. The test voltage is raised uniformly from 0 volts to, you know, to a specified value within 5 seconds. Pretty much, this is kind of some details on why 500 VA is called out in certain standards. Not why, but how. This is how it's read in certain standards, right? They must pass the 200 milliamp short circuit test, meaning if that transformer, forgetting firmware, forgetting any software control, that transformer alone inside your Hipot tester, if I short it, how much current can I get from it? And why do we want that? Well, the reason, well, I'll leave the slide for you here, and if you want to review it more, Brittany can send you a copy of it. But the purpose of it is that you don't want some sort of load on your, a DUT, a load that draws a large amount of current, and now is a large voltage drop is seen on your DUT, and because that transformer doesn't have enough power behind it, the voltage starts to dip, and you're not truly testing at the test voltage called out by the IEC standard. That was kind of the idea behind the 500 VA testing. So energy and breakdown, right? Originally this was required to ensure high voltage output remains consistent. The higher the transformer, the more current we can output, right? So that's why we have 100 milliamp testers. Now, most associated research instruments have about 500 volts output. Thus, if it's a 500 VA, I can give you at least 100 milliamps of trip current, right? And while you'll never see the 200 milliamps because we control that via, you know, our firmware, just the transformer by itself, we kind of guarantee, or we've tested or we've complied to the 200 milliamp short circuit current rating. Now here's the whole purpose of behind that, right? We have unregulated Hipot outputs and regulated Hipot outputs. The issue is on unregulated Hipot outputs, that output is so dependent on your input voltage, right? If I'm going to have you know, up to 1200 volts or 2000 volts, well then you better be giving me the high side of my input rating. Where our Hipot, the Associated Research Hipot testers, we have you know, a feedback board that allows that output to stay consistent, to maintain, to keep driving, regardless if you're on the low side of your input value or on the high side of your input value. So now as technology has evolved, and to be honest, most Hipot testers are designed this way with a regulated output, that 500 VA necessity and standards, it's kind of becoming obsolete. And so in a lot of standards today, you know, these days, they're starting to chop that out. They're starting to say, you know, you no longer need a 500 VA, or at least we're in the midst of that. We're in the midst of that. We actually, you know, have some of our colleagues on certain standard boards, and they're trying to get rid of that 500 VA because it's just, it's outdated. It's no longer needed. With the technology we have today in Hipot testers, your output, for the most part, can drive and stay consistent. Excuse me. So now let's talk about how to set leakage currents, limits. Okay, this is kind of what I referred to previously. You know, for someone who's just getting into Hipot testing, there's so many parameters, it's probably a daunting task to try to understand how to set that, right? So we've talked about the important ones. The important one is voltage, right? If you're not sure, it's not called, you haven't got that info from your standard yet, or your, NRTL, nationally recognized testing lab auditor or engineer, take 2 times your rated voltage plus 1,000. Okay, great. Now I know what my test voltage is. What are my limits? Now we'll discuss how to set your limits, right? What I would do is perform Hipot tests on known good products, and you want to start recording these results until you see consistent numbers, or at least a consistent average, right? Something that you're comfortable saying, the characteristic of my product is to leak this much during a 1.24K Hipot test. Now that you have the average, well, depending on how you feel about your manufacturing process, how uniform you want it to be, you can take 25% of this number and you can add this to that number, right? So multiply by 1.25, set that as your high limit. That way sure, I'm not breaking down, but if I have some insulation that's leaking a lot more than I expect of my product, you will at least be notified of it, right? Does it mean you failed? Yeah, it'll say high limit failure, but as far as the standard's concerned, you didn't fail, right? No breakdown occurred. But internally, your internal quality, you now have noticed that, hey, this product is a lot different than the rest of my products. Let me investigate. And same thing on the low limit side. Well, what I discussed earlier, right? Sure, it's great that this product is leaking a lot less than everyone else, than all the other products, but why? That's the question I'd want to know. Why is this one so much better than the other ones? What in the manufacturing process is different on this guy than the rest of them? And it also gives you that peace of mind that, hey, my operators are accurately making connections. Worst case scenario, right? You forget to return a connected return clip. You obviously pass your Hipot test because, again, you're just testing air, which is going to pass. Put it in a box and ship it without ever really being tested. So here's an example. If someone tested 10 DUTs, on average, leakage was 5.5 milliamps. I'd set my high limit at 6.88, my low limit 4.13. Now I have a nice window where I expect all my products to fall within. Now here is what I was referring to, these special features that we've developed during a DC Hipot test to make it a lot easier for you. Ramp high and charge low. So I have a product that I've attempted to test in AC, but because of the capacitive nature of my product, I keep failing because that reactive current is there. And so, whether it be a high limit that's set by internal qualities or a high limit that's set via the standard you're testing to, I keep failing. So now I'm told we'll allow you to test in DC. That's great. So I convert my voltage from the 1.24K, I multiply that by 1.414 or the square root of 2, pretty much the way to find your equivalent DC voltage from AC. I've set that as my new test voltage for DC. I hit test and I'm still failing. Why am I still failing? Well, reactive current only occurs when there's a change in voltage, right? And it occurs at a higher rate when I have a change in voltage in a short period of time. Well, for one moment in a DC test that happens, right? When I go from 0 to that 1780, I said, I'm applying a large change of voltage to my highly capacitive product. Well, that's going to draw me a large amount of reactive current momentarily during that ramp up. So there's a few things you can do, right? I can increase my ramp time. Let's make it 5 seconds, 10 seconds. Well, now you're testing each product at 10 seconds, which in the manufacturing process and production, it's you can't do that, right? We need to ship these out as quick as possible. So we've developed this feature ramp high, which what we state is during the ramp period, we will not fail you. Okay? Because if you're truly leaking an amount that should be a failure, well then guess what? You'll also leak that same amount during the dwell time. The dwell time being your actual test time. Okay? So if I can get you, I'll get you through that ramp time to get past your capacitive qualities of your DUT. Now during the dwell time, we'll measure your real results, which those real results are purely resistive and will probably be very close to zero. Okay, so I need to distinguish how our ramp high works in separate instruments, certain instruments. Now, when ramp high was first introduced, we stated, you know, we won't fail you during ramp high. What does that mean? That means, hey, I'm going to allow you to draw as much current as my transformer can provide, right? I mean, if that charging current is so much that even the internal transformer of the Hipot tester can't provide, well, it's obviously going to shut down. I mean, it's going to protect itself and shut down. But if you're within that range of the capabilities of that transformer, we will allow you to have that much leakage during your ramp up time. And what's great about the new 7850, our new Ultra series, is that's also a settable value. Like, yeah, I understand I have a large amount of inrush current or a large amount of reactive current during my ramp up, but I didn't think it would be that much. And so now you can regulate that. That's a settable value now. Hey, I know during dwell I'm not supposed to leak more than 5 milliamps, but during ramp up, I still don't expect to see at least 12. You can set that 12 milliamps, whatever it is. Again, just gives you a little bit more control, but now also allows you to go back to testing at 1 second, at 2 seconds, at 3 seconds. You don't have to extend your test time. So charge low kind of is on the opposite spectrum for this feature. Earlier I discussed how a low limit works, right? A low limit is great because if you leak less than that, well, that'll let you know maybe an operator forgot to clip something, a return clip, while the test passed. You may have never really tested it. Well, that becomes an issue in DC testing. Why? Because, like I stated, once you get past that reactive current and you're in your dwell time, your leakage is going to be very close to zero. And so how can I create a low limit? Set my low limit to how low do I need to go if I'm going to be so close to zero? That low limit almost becomes obsolete in a DC test. And so, great, now I'm passing DC, but now I don't have the peace of mind that I know my operators are connecting properly because my low limit has now become useless to me. It's obsolete because I have really good insulation and I leak very little during my dwell time. And so what we've created is this charge low feature. What that does is it will monitor that peak during ramp time, and I'll say, okay, I know how much that peak is, so I will set a charge low value to maybe half that. And so next time you run a test, I become your new low limit. Charge low becomes your new low limit. Hey, I just saw that inrush of reactive current. I'm going to maybe divide that by 50, and on your next test, I expect my reactive current to definitely surpass that level. If you don't surpass that level during your ramp time, then you probably didn't connect anything because I didn't get that quick reactive current. And so charge low has now become a quasi-replacement for your low limit. So these features are used with a DC Hipot tester or an IR tester. Charge low is available on IR. Due to the nature of the DC withstand test, again, high limits and low limits can prove difficult in these tests because of that reactive current. So these features compensate for this difficulty and allow the user to properly monitor these limits. So I believe that was the last slide of our presentation. It was a lot of information to digest, I know. We might have sped over some of it quickly. So if we did, feel free to contact Brittany at brittany.soha@arisafety.com. I think we'll leave some time here. If Bashan feels there was any relevant questions we can discuss. I can look through an example. Okay, here's a question. Can you give an example of a highly capacitive product? So Bashan says a spool of cable, right? People aren't going to roll out a long piece of cable to test it. They're on spools. Well, those spools have now created a plate, a metal plate on another metal plate on another metal plate. And so now you have large capacitive buildup, capacitance charge built up on that DUT. And it's important to know that you will get capacitive charge, but also you're going to leave a lot of charge on that product. So using your ramp down feature on a DC Hipot test is also necessary, right? Because you want to make sure you discharge that product, and if you don't want your test time to be longer, well then have they're called hot sticks, right? A discharging stick, something that is conductive, that has something dragging at the end of it that touches ground, so you can dissipate all that charge to ground. Let's see. Another good question was, is it possible that relays and capacitive components on PCB can affect the Hipot test? And so um, this is important. Are those relays closed while you're testing? Are they open while you're testing? You want to make sure those relays are closed while performing a Hipot test. Otherwise, again, if you have a relay that's between your line and neutral, well, if it's open, you're going to pass, right? You never, now you're just testing between the one side of the relay and technically everything that's on the other end of your return. So that's a good question. If you do have a product that has a switch, make sure, while it's not powered on, make sure that switch is in the on position, so any relays necessary to short that line neutral are closed. Okay, I think other than that, we should be good. So with that, I want to say thanks for everyone attending this webinar. Again, if you have any questions or concerns, feel free to reach out to Brittany. I apologize for any coughing or disruption while the webinar was occurring, and please feel free to reach out to us with any questions, and join us for our next webinar, which is the second most popular test, ground bond and ground continuity. And Bashan will be presenting valuable information on that topic. Okay, so unless we have anything else from Bashan and Brittany, this is Anthony signing off. Appreciate you joining us, and we'll see you again soon.
We're going to keep it open just a little longer because Bashan is still answering some questions.
Okay, great. Okay, so here's another question. One of our attendees says they have a dwell time for 60 seconds at 1500 volts, or you can do a 1 second test at 18,000 volts. I'm not, that might be 18. Well, right, so it's still the same thing, right? You're either testing your insulation at a lower voltage for a longer time, or you're shocking that insulation with a large amount of voltage for 1 second. Either way, you're testing the quality of that insulation, and a lot of standards will write that in because maybe someone can't do a 60-second test, they need to do a 1 second test. But if you do want to cut that time, well, now you're exposing your insulation to a lot more voltage, and that can cause issues, right? A brick wall can take a huge punch once, but if you give it that same punch twice, you might puncture it. So there are some causes or some wariness, right, in bumping up, just because you want to save time, bumping up the voltage to a higher voltage, because of excuse me, because eventually you are going to start degrading your insulation on a product that you're about to ship out. So those are questions you might want to ask internally if it's worth it. We also have some requests for the Architect white paper, so we will have Brittany send that out to those who ask for it, and um, we will also make sure it's on our website because it's valuable information, and it's a it's an important feature on our product that isn't utilized as much as maybe some performance testers, engineers in that phase would want to use. Sean asks, when a product fails a test, is it reasonable to repeat tests while disconnecting specific parts of the product in order to determine the source of the failure? Um, that's a great method to identify where the failure is coming from if you're in an investigation phase. But at the end of the day, you need to make sure that that part of the product is either replaced or upgraded so that it can pass as a whole, because you're selling the consumer a complete design product, not just a bunch of parts put together that pass. It all needs to pass together. Just you modify one thing on a product, you've now lost your CE listing, your UL listing. So it's important. It's a great way to investigate why you're failing, especially if you're trying to get that listing, and work from there. Okay, I think Brittany, if it's all the same to you, we'll go ahead. Bashan has everyone's information, so we do still continue to answer these questions offline. Um, and until the next webinar, Mrs. Anthony, appreciate you hanging on with us, and hopefully you found this information useful. And please join us next month to discuss ground bond testing, which is also a very highly effective way to test your ground circuit, but dangers do come along with high current being output. So safety for your operators is very important in that topic as well.
All right, sounds good. Thanks, Tony. Great job.
All right. Thanks, everyone. Have a good day.